Hello, everybody. Today's topic is going to be using. I'm crying. What the hell? Is going to be using gravity as energy. Now, as we did on the first lecture on gravity, we reminded everybody that the potential difference can be found by taking the integral of f dot dr, and since we're only working in radial directions with gravity, this change in potential turned out to be big G, mass of one of the objects, mass of the second of the objects, divided by r, and negative. Then we made a quick plot of the energy and the distance, and our gravity is a 1 over r dependence. Okay. Notice that along both axes, a 1 over r dependence asymptotically? It's something like that. Gets closer and closer to the axis without ending. So let's put this into work in a simple case of escape velocity. So let's do escape velocity. And to do so, we're going to use energy. And that means I need to find a system, which would be the Earth and spaceship. Notice that on this graph, I will have a radius of the Earth. So at a practical level, we can't ever get to zero on the smaller and smaller side. There's some fun problems with that, but we'll deal with that when it comes. But the r distance, as we send r to infinity, that means both the force, which is g m1 m2 over r squared, that force will go away, that you are so far away from the Earth that you don't feel any gravitational effects. Likewise, the potential energy is going to go away. So minus g m1 m2 over r. It's also going to head towards 0. And that's the idea of the escape velocity for our spaceship. Our spaceship's going to start on the Earth and then move against this potential until it has escaped. So this is our initial place, and up here is our final. This is where our ship ends up. Okay. So using that, let's go in and solve our, everything's out of control. Let's go in and think about what that means in terms of energy. that if my system is the Earth and the spaceship, I have final here, I have initial here. Our idea is that we're going to have a kinetic energy that's going to need to overcome the Earth's gravitational potential energy. And if we've done it with the kinetic energy equaling 0, and we're at infinity, then we are looking like we've got the minimum possible speed. And that's what's meant by the escape velocity. So we can calculate this with energy. Our energy final is all 0. Our energy initial is the kinetic energy of the rocket. Minus the gravitational potential energy, Gm of the Earth, m of the rocket, divided by the radius of the Earth. And when we do delta E then as equaling 0, my E initial is the only thing with terms. So I get 1/2 mass of the rocket, V minimum, equals G mass of the Earth, mass of the rocket, over the radius of the Earth. The mass of the rocket turns out to be irrelevant. And what's nice about this is, we'll finish this, V minimum is going to be equal to 2 big G mass of the Earth, radius of the Earth, all that under a square root. So this is the simplest way of putting it. This is the velocity you would need to leave the surface of the Earth and hit a point where there's no more force pulling you back from anywhere else. So it's just the Earth and the spaceship system. Consider that as we talk briefly about orbits. So this is going to be our first discussion of orbits. And it's going to be orbits as circles. So what we need to envision is, let's do the Earth, big blue marble. Anyway, and then we want to set up a object in orbit around the Earth, and its orbit is going to be a circular orbit. To solve this one, because I'm only interested in a single location, not two different locations, I'm going to dive into forces. Some of the forces, mass and acceleration. And I only have forces that are going to go, so when I draw my free body diagram, the only force I have is the force of gravity pulling it in. So I'm going to wind up with the force of gravity equaling the, wait, something's wrong. Oh, yeah, we have to put in our acceleration, and we should probably choose a direction. So now the force of gravity is equal to mass, and we have a center pointing acceleration. The force of gravity, G, M1, M2, over d squared, where d squared is from the center of the Earth to the center of the other object. And, okay, that's going to equal mass and v squared over that same d instead of using r. The mass of our system would go away, and then I'm going to wind up with let's see, I got to multiply both sides by d, so we're going to wind up with g m1 over d. That's going to be under a square root, and that will be the orbital velocity. So when we compare the escape velocity, everything under v min is set, meaning that the mass of the planet, the radius of the planet, g and 2 are both absolute numbers. When we're talking about orbital velocity, sure, it's based on big G, mass of the Earth, but d now is any altitude you want, any distance from the center of the planet to wherever this object is. And even though it looks similar, with g and m and a distance, let me highlight what I was talking about, with g and a g, and then we have a distance below, that's a distance, and then we have the mass and the mass. It looks like the same form, but this 2 is going to make it slightly larger than you would get if you were just buzz bombing the Earth, where d was equal to the radius of the Earth. So we'll spend more time with orbits in the next lecture.